Good afternoon and welcome to this afternoon's Plant Engineering webcast, 5 Ways to Achieve Machine Safety Without Sacrificing Performance, sponsored by Schneider Electric. I'm Bob Vavra, Content Manager for Plant Engineering. Thanks for joining us today. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you're having technical problems with the audio or the slide presentation, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you're experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Technical questions will be answered in the Answered Questions on the left-hand side of your screen. You can use the Ask a Question box on the left side of your screen to type questions for our speaker during the presentation for our Q&A session at the end. You can ask questions at any time during the presentation and we'll get to as many as time allows. To download the presentation slides, use the Event Resources tab on the left-hand side of your screen. Now we're going to hear from the sponsor of today's webcast, Schneider Electric. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation.
The Internet of Things is changing the game. To meet the challenges of today's digital economy and gain a competitive edge, industrial companies need to fully embrace the capabilities of new IoT-connected technologies. That's where EcoStructure for Industry comes in. Uniting the worlds of automation, connectivity, and software, EcoStructure enables you to drive the evolution of your business, rather than just plan for it. The EcoStructure open architecture integrates connected products, edge control, and apps, analytics, and services to help companies unlock new levels of productivity and efficiency. This may sound challenging, but EcoStructure for Industry makes it easy, providing businesses with real-time control and IoT data. It empowers operators, enables proactive asset performance, and ensures agile management. With leading industrial software that's open and integrates seamlessly with most industrial systems, you can enjoy tangible benefits regardless of which equipment you have installed. Today, 2 million licenses of the platform are installed at over 100,000 sites, 20 billion operating parameters are monitored, and 4 trillion transactions are processed and stored every day. By delivering innovation at every level, EcoStructure for Industry is empowering businesses and transforming industries all over the world.
We're very pleased to welcome our speaker here this afternoon, Jason Kimball. Jason's been in the industrial automation space since the mid-1990s, joined Schneider Electric back in 2000. His early experience was mostly hands-on automation and control projects, including on-site power generation, boilers, HVAC, water and wastewater treatment, chilled water, printing, and material handling. He joined the technical support group for Schneider Electric AC Drives, which eventually led to a role in product management and marketing. Since coming into his current role, some of the products Jacob's worked on have been included operator interfaces, machine PLCs, and machine functional safety devices. Jason, good afternoon, and welcome to this afternoon's webcast.
Thank you, and thank you for joining us today. Let me just go ahead and get into the session. Basically, today we're going to talk about achieving functional machine safety. Couple focus areas here just to keep in mind. It is mostly focused on machine safety. A lot of what we talk about here, it's relevant in process as well. Just again, this is mostly focused on the machinery itself, which is a slightly different set of standards. And also, we're really not just looking at like the technology from an engineer point of view of how to do it, but really focused on how to be productive, how to keep our processes running, and that sort of thing while managing machine safety. So what we'll do is we'll look a little bit at the standards because it's important to understand what's required of us. Again, when it comes to the standards, it's not going to be a super deep dive into it. In reality, there are 3 to 5 day long training classes that you can go to, where at the end of it, you may or may not qualify to be certified as a machine safety engineer, for example. And clearly, we're not going to go into that level of depth. The point here is to highlight what is relevant from an overview perspective and how that can be addressed in a way that really helps us to be productive with our operations. And so that's what we're going to do, including looking at some of the technology advancements that make that easier to manage. So as I kind of stated, it's important to know the standards. And so as we look into those standards, we will see how that's relevant to us. There are a lot of different organizations and associations that write standards and they write processes, so it can get pretty complicated to even just list them. But we've probably all heard of them before. OSHA, for example, and the National Fire Protection Agency. Most electricians know this one pretty well because of the National Electric Code, but there are some very specific standards that relate to machine safety that they manage. Robotics, that's clear. Obviously, if you're dealing with machine safety, robotics is a growing industry, so RIA is very helpful in helping to define risk assessment as well as practices of addressing the risks with functional design. ANSI, it's an American-based standards organization, so very relevant to us. For sure, you're going to have questions from customers, end users. OSHA is going to refer to ANSI, so it's another organization to be familiar with. And then we kind of get into a couple that surprise some people, but if you've been working with safety for a while, it's not as much of a surprise. But ISO and the European Commission are European-based primarily, but they're very relevant in the U.S. as well. And a lot of times that's because of global reasons. Obviously, we are importing, exporting machines, but then there's also our customer base. For example, I work at Schneider Electric, which is a very large international company. So if you were doing work in one of our locations, we would probably have some requirements that are global. And so these international kinds of associations and organizations are very relevant. But as we look specifically at the United States, the one that we usually care about the most, by far, is OSHA. And this is because OSHA is not really just a set of standards or guidelines, but it is actually the enforcement agency that makes sure that we are complying with whatever guidelines there are. And what I highlighted here are the words safe and healthful working conditions. So that's what OSHA is striving for, is to enforce that. So they can levy fines if we don't comply, or worse yet, we have some kind of an accident, some harm is done, and they can shut plants down, stop production. So OSHA is the one we always think of when it comes to that. But in reality, they're a relatively large organization. Things don't change quickly because of the complexity of things. And so they rely pretty heavily on the other organizations that I already mentioned, whether they're U.S.-based or international, because the RIA, for example, or ISO have written some very modern, very comprehensive methodologies when it comes to doing the risk assessment, but also design criteria and doing testing and validation. So OSHA will rely on us to be familiar with industry-leading documentation that we apply to our particular application. So OSHA, most important, but probably not the most referenced when it comes to the engineering practices that you're actually going to use. Usually it's the other organizations that you're going to refer to a little bit more technically. So how do we put it all together? What do we need to actually do to achieve a healthy and safe workplace? Well, it might depend a little bit on who we are. So a machine builder is going to try to build safe machines because the market requires it. But ultimately, it comes down to whoever's in the United States for sure. It's the employer who's going to be most responsible for it. So how do we physically do it? Well, let's look at a couple examples. This is pretty simplistic, but it's on purpose because I'm going to try to use this to illustrate the 5 steps that we can apply that will help us to be more productive in safety. So as we look at this, that's why there's simplicity here. So if you have a hazard, one of the first things, the simplest things that comes to mind is to do something that prevents our operators, our maintenance people, people from coming into contact with the hazard. So in this little picture I have here, a saw blade. Easy to understand. There are all kinds of different kinds of hazards, right? There's things that bend, that twist, that drill. It might be really hot. There could be chemical exposure. But whatever it is, the first thing that we usually think of is taking that hazard and making it impossible or very, very difficult for somebody to come into contact with it. So sometimes we loosely call it putting it in a box or guarding it, blocking access. So that is a very, very effective way of managing a hazard. And we'll get deeper into that a little bit later. So a second way of doing this, it's very common, possibly in the right order here, maybe the second most common, is to kill the power. So you have some kind of hazard. We're talking about automated machinery here. So most things have a source of power. Electrical is the most widely used, but it could be pneumatic, it could be hydraulic or something else. Whatever that is, if you can kill the source of power whenever there is some kind of hazard that the operator is at risk of coming into contact with, then you've done an effective job, as long as that machinery can shut down fast enough to protect the person. So that's kind of the second one. And the third one seems a little bit similar at first, but it's to stop the machine. And I think I would emphasize on here, it's shutting everything down, all of it, right? So, and it might not only be killing the power, but it could be turning off controls. And the way I have it pictured here is like an assembly of machines that are all associated with each other. And if something goes wrong, you shut everything down. And that's very, very common. It's kind of simple to do. And so it is a commonly used way of doing things. And this is especially used when we're talking about an emergency stop button. And really, it's hard to say that that's a bad idea. An emergency stop button is a little bit different than what I usually and what a lot of people consider functional safety, because now you're talking about potentially something already has happened and they want to stop everything. Usually when we're talking about functional machine safety from a design perspective, the stop button is probably still going to shut everything down. But we also seem to employ that methodology frequently for automated portions related to our functional safety as well. So these are very common. Block the person from touching it, kill the power, and shut everything down. But is that the best way to do it? Well, obviously I'm asking that question for a reason, so you can probably already guess that the answer is no. But let's look a little bit more specifically at that. So first of all, if we talk about putting the hazard in a box or totally blocking somebody from coming into contact with it, there are some downsides to that methodology that affect our performance. So one of the things that's pretty easy from this picture is that sometimes you cannot see what's going on. Now, you could use a clear cover and then you might still be able to see in, but this is what am I trying to say here? It's not what we want to do usually. We don't want to totally block people from being able to see or touch the moving parts of the machine, because something needs to be done. So either we're moving materials in and out, there are times where we need to make an adjustment, and if you've got it totally blocked out, that's really hard to do. And so when somebody does need to access that area of the machinery, it takes time. They have to defeat that blocking mechanism somehow. And if you're doing that, it's wasteful, right? So now looking at the second point, when it comes to killing power, pretty easy to see what could happen here is that if you're dealing with automated machinery, if you remove power, you also remove your communications. If you're doing some kind of logging or tracking of the status of the machine, operating it, you lose control. So that's not very desirable. Plus, you might have wasted materials because you're not controlling the shutdown, and then you need to restart it. And depending on what sequence of operation you were in when you had this complete removal of power, it may not be convenient to restart. It's going to be expensive in some way. So, and the third way of dealing with things, which is shutting everything down, it kind of has similar downsides as killing the power. You're probably going to impact your productivity. There's very frequently there's lost materials. In something where I show like this assembly of machines where parts move from one part to the next, to the next, to the next, things back up, fall on the floor. It's costly. So we're thinking about safety first, but when we just employ these simple methodologies, we also realize that there's a cost. And so this is something that we want to improve upon. So the end result of these three common ways, very simplistic ways of dealing with machine safety is time lost or materials. Either way, it costs money. So you probably already know all of this. As somebody who's been involved with a lot of meetings with people who are actually trying to employ new designs to their systems, it is those three reasons that I just talked about are what we have to face when we go into the conference room with the plant manager and other people that are really interested in productivity, because it's an obstacle. They're going to be spending money because they have a reason to improve their safety, but right away we're facing headwinds because of the cost of doing things, I'll just say, the old way. So what do we do about it? We can definitely do better if we think about optimizing our approach to the machine design. It usually requires that we take a step back. So here's some simple answers, that are included not just in a logical way of looking at things, but they're written into a lot of the standards. And I cite a few of them here. There's really quite a few to consider. But let's look at this first point. Instead of putting a box around the machine or completely blocking it forever, totally, one thing that we can do is employ removable guards. So maybe they're hinged or they're sliding. It's doors that open and close. And in all of these cases, if they're automated, what we're usually looking to do is to sense whether or not those doors are open and closed, so that the control system can respond accordingly. If access is allowed, in other words, if the cover is open, then probably at that point you're going to have your functional machine safety automated controls turn that part of the machine off, right? So conversely, in addition to sensing, there are also tools that allow you to lock those guards, lock those doors, so that when it is operating, you can't open it. So that's what we're trying to do. Make it movable, make it controlled access instead of completely denied access. So we can picture that. If you look here, you can see two pictures of the same door that slides up and down. And on the bottom right, you can see a couple red components, and those are just sensors. They're not there to lock the door, but they give the machine and the safety controls inside the control panel a reliable, tested, certified method of ensuring that we recognize whether or not that door is open and then respond accordingly. And I mentioned already, there are other things to consider when it comes to controlling access. And one of them is to actually keep the door locked using interlocks. And interlocks are really nice because they do kind of two jobs. On the one hand, the interlock is usually at the point where it can sense if the guard is open or closed. So if the door is opened, it will interact with the controls to shut off the hazard. But they're also interlocks, so most of them have a way to lock the door, lock the cover, so that it really cannot be opened while the machine is running. So they serve both of those purposes and help to prevent, accidental restart, and really to help enforce properly accessing the hazardous area, making it easy. At the end of the day, you don't want to make it hard to get to the place that has the hazard, as long as you can make sure that it's safe. That way you don't have people trying to bypass it, trying to remove sensors that are there for their own protection, and that's something we want to keep in mind. Another little footnote, because I didn't really put it on here, or a picture of it anyway, is that a lot of the standards that refer to controlling access also cover things like light curtains, which don't prevent materials from moving in and out, or people, arms, hands, from moving in and out of a hazardous area, but they also are there to help with that control of the access and to shut the machine down before a person can come into contact with it. So some of the standards that apply are listed here. ISO 14119, for example, and other standards like that talk about the design of the products themselves. And then, of course, there are plenty of standards to talk about how to do the risk assessment and the implementation. So moving on to the second point that we talked about. The second way of controlling things a lot of times is by killing the power. So instead of killing power to the whole machine, one more controlled way of dealing with that is to isolate, to understand specifically what controls the hazard that is under consideration, and just shut that down instead of shutting the whole machine down. So as the diagram shows here, there's going to be a number of components that interact to do that. It shows a gate, but it could be other things. There'll be some kind of sensing of the hazard or the presence of a person in a hazardous area or a condition that could cause harm to somebody. There'll be some kind of relays or controllers that are going to analyze that and then shut that part of the machine down. So what I show on the right-hand side is stop category 0, and there's a reason for that. The most common thing we do is remove power from the controller or the motor starter that is running that part of the machine. But we can also do other things. So when we think about controlling the hazard, it's not always removing power from the motor or the actuator, whether it's electrical or pneumatic or whatever. Sometimes it's actually controlling it. So there are applications where it's desirable, rather than removing power, to have the motor or the robot arm, the servo, to actually control the stop or even control it to a certain speed or location. So those can fall into categories 1 and categories 2, which have some level of maintaining power, maintaining control, rather than just completely eliminating it. Now, you don't automatically go into categories 1 and 2 just because you feel like it and just because you want more productivity. It does affect the level of probability before dangerous failure calculations that you'll do when you're comparing your design with your risk assessment results. So, but it is good to know, that there are ways that you can sometimes employ that even allow for a controlled stop instead of a complete stop, especially if you're looking at productivity. Another thing about that is that a lot of products have that kind of technology built right into them. So AC drives for controlling asynchronous motors, and as well as servo motors and robotics controllers are already doing a very good job of being precise in their control of the motors. And because of improved technology, the feedback from the motors and from the encoders, for example, and position sensing devices is able to be tested and certified to such a degree that those motor and motion controllers can actually handle safety functions directly on them. So that's something that can save money. A lot of times you're talking about a component that you already have anyway, and adding the safety functions Well, sometimes it does not need to be added. It's just a matter of understanding how to use it, how to wire it, and configure it so that it can help you to be safe and also productive at the same time. So keep that in mind when you're looking at those kind of automated products, that there may be some built-in safety features that you can take advantage of and help control your stop and your restart. So the third thing that we looked at was stopping everything. And the reason I mention that is that what we want to do oftentimes is think about using logic. So what we're doing here is a step beyond just isolating the offensive area or the hazardous area and stopping it, but really we're looking at the whole process. How are things working together? What is the sequence of operation? How does timing affect it? And we want to do different things under different circumstances. So we're usually looking here at something like a safety PLC. That's the first thing that comes to mind, because a PLC is a programmable logic controller. And if you're thinking about employing logic into something automated, it needs to be programmable. And that's why we think about safety PLCs. So, but there are also other technologies that are closely related, such as safety controller. We'll talk a little bit more about that. So how does this get implemented? How can we help ourselves be more productive? Well, I've got a little scenario here. And I'll start with the simplest thing first. If you have that assembly of machines where it looks like we have 5 different machines, maybe 6 different stations in this assembly, they're all working together, but they kind of are all separate machines, maybe even made by different manufacturers and locally installed. Well, usually if you hit an emergency stop anywhere in this assembly machines, and I'm not saying this is a rule, but typically you're going to shut everything down that's associated with it. And that's because if a person's hitting that e-stop, you don't really know where the problem is. Somebody said help, and somebody else said stop, right? So you shut all the associated equipment down. It's the right thing to do because you don't know how to isolate it. So that's easy to see in an emergency stop circumstance. But now the same assembly of machines, what if somebody opens up this little window on a machine that's kind of in the middle of this assembly? Well, if you open up that window, you're doing something there. And if there's a hazard in that place or in that machine, in that station, obviously you're going to have to react to that hazard and the fact that somebody has now opened up the door and they're going to put their hands in there. So you shut it down. Logically, that's what you're going to do. But all of the machinery that's coming into it, you might need to do something. So I kind of color it in yellow, meaning you need to think about it. Can this cause a problem? Maybe, maybe not. It kind of depends on how the materials flow. But oftentimes there's not really a safety issue. It might be more of a production issue. So you're probably going to do some kind of reaction on the inflow side of that opened window. On the outside, or on the like the effluent part of this machinery, you might not need to do anything. Everything that you've processed in that kind of middle area, it might be okay for it to continue going on. We're not talking about a quality issue where we need to reject materials. So you might as well continue with the operation and keep production going. And depending on how these machines interact with each other, it could be that by the time you do your work and close that window again and restart it, the impact to your overall production is very, very low, or perhaps nothing at all, because you can continue as you go to the exit side of that machine. So the reason I illustrate these two things is that in the emergency stop scenario, you're going to react one way. You're going to shut everything down. In this other scenario where you're accessing a specific part of the machine, the logic is very different. You're going to be affecting things in 3 different ways. And it might even depend on other things like what time it is or how fast the machine is running. There's going to be other things to think about, but it's already simple enough. There are 3 different answers. So logically, if you were to use, a logic flow chart like this one I have here, handling the e-stop is a matter of having the e-stop affect all of those three parts of the machine the same way. And if you're using something programmable like I'm showing here, then if you come up with a scenario where the reaction is different when somebody opens up the door, this is how different the logic is. It's really not that different at all. It takes like 10 minutes to do the programming. And of course, you're going to spend more time in testing and validation and make sure that the sequence of operation is good. But this is really easy. There's a good chance you don't even change your wiring at all. All your sensors are still connected to the same place. Your motor controls or robotics controls, whatever you're doing, are all on the same outputs. You've changed your logic. And now you have a way, even on your HMI or your SCADA systems, whatever your operator is interfacing with, to even know, hey, this door is open, so I'm in the door is open mode, which means I'm doing this and that, right? So you can help your operators really understand what's going on because you have this logic that was pretty easy to engineer, and it's electronic, it's data-driven, it can communicate very well with the operators. So anyway, this is just to show that using logic is is the preferred way of dealing with these more complex applications, and it's easier. So imagine, I don't have a diagram here, but could you imagine how different the wiring would be between the emergency stop shuts everything down scenario versus in some circumstances, I'm going to slow something down on this part, but the other part's okay, and I want to shut down this middle section. The wiring, if you were to just use relays, would be impossibly difficult, and you don't really want to do it. So you use something programmable. So one of the things I wanted to mention here, because we're talking about improving productivity and being profitable, is that there is kind of a newcomer in the market, and I say new meaning probably only about 10 years. I mentioned earlier that when we're talking about logic, we usually think of a safety PLC. Well, modular safety controllers, or I'll just simplify that to safety controllers, are a little bit of a newcomer to the market, and they're a little different than a safety PLC. So as shown here, we have a PLC, and in the picture it's gray, and then you have a safety controller, which are the red portions. They're both programmable. The PLC, or the programmable logic controller, its primary job is to run the process, run the machinery. The safety controller, its only job is to manage the safety. They're both logical. Obviously, an engineer who would be working on this would want to consider the sequence of operation, and there's a measure of interoperability between these two components, but they're not in the same product, and they're lower cost. The codependency of these products is not as strong as with a safety PLC. So it's not always the right answer. I'm just mentioning this as being a lower cost way of dealing with a lot of medium complexity machinery where there's safety logic needed, where we tend to jump to the conclusion that we need a safety PLC. This may be a simpler way to do it in many cases. And all the manufacturers that I know of, pretty much, since I work in Schneider Electric, this is not an advertisement because the manufacturers have this. I just want you to be aware that this is a nice middle ground way of dealing with logic. And of course, safety PLCs have their place, and they continue to be probably the primary way of dealing with logic and safety, especially in very large machines or complex production and plant and process applications where safety and the process itself are very, very closely tied together. Or the application is actually installed on site. Very typically, you're going to be dealing with a safety PLC in that application because of how closely they're tied together, and also because cost is usually less of an issue than it might be when you're a machine builder who is trying to sell machines to a customer. And then you'll usually see a safety PLC on installed on-site kind of applications. So we talked about safety logic with programmable products, but just to be aware too, the reality is safety relays are what you usually see inside a control panel. So this is probably something like 70 to 80% of the time. If you open up a control panel, there'll be a PLC in there controlling everything, but there'll also be relays. And relays are very good. They don't have that kind of programmable logic capability, but some of the newer relays do have a little bit of logic in them, and sometimes it's enough. It could be as simple as dealing with timing or verifying that two separate conditions, including position and speed, are coordinated so that you're controlling really usually a single output at a time, like one motor, one relay. Now, it's not exclusively that way, but typically the relays are a nice simple way of dealing with a simpler logic. I kind of say to myself, if you need 3 or more relays, you probably should have used something like a programmable safety logic controller. But that's just, a rule of thumb that I use because if the complexity gets beyond 2, 3, 4 relays, then, doing something programmable is probably going to be less expensive and easier. But most of the time, it's relays that you see in the control panels because it covers most of the need. There's also a lot of products out there where you have a regular PLC, I'm going to call it, and you can add safety logic to it. Sometimes it's as simple as what I show here, which is basically a relay. And the advantage here is that you have the ability to see the status of that safety controller or the safety relay without needing additional wiring to your PLC. But there are other products. I'm not showing all the pictures that are available. There are other safety modules that can be added to PLC systems, some of which are more remote, and they are programmable, and they do have logic employed in them. Some of them are designed a little bit more for process. Others are more for machines, especially around robotics. But that's another thing to be aware of, too, is that some of your standard PLCs can have safety functionality added to them. So the end result of considering this is that we are looking for ways to make the machinery easy to use. So as we're designing our machines, as we're designing our processes, we may have a little bit more work to do in our design process, but we're trying to make it easier to use. And then that results in time saved, material saved, and money saved. But there's also a couple other ways that we can improve our productivity when it comes to safety that are a little bit different. So everything I talked about here about controlling the hazard, more directly, about controlling access with sensors and interlocks so that you're doing smart shutdowns of things and using logic, those are what I'm going to call a little bit more hard engineering, like brick and mortar, if you want to call it that. It's physical. It's what we're used to doing. But because of the Internet of Things, the industrial Internet of Things, there are some other ways that we may be able to expand our horizons a little bit, think outside the box, and consider productivity, not just safety. And they need to be together. So an example of that is being able to use some means of augmented operator, operation. Sorry, I was being redundant there. But, augmenting your technology where you're able to use something like a phone or a tablet at the machine location. It has intelligence to see inside the machine. Obviously, that's been pre-programmed. It's not using science fiction to figure it out. But with our engineering help as engineers, we know what kind of tools the maintenance person might need, or the operator, or even a shift supervisor might want to see. That's usually hidden. So we see this a lot when it comes to troubleshooting. Before I was in Schneider Electric, I worked in electrical maintenance, and I worked with some medium voltage equipment. You sure don't want to open up that door while it's live. If you do need to open it up, you need special equipment that you're going to wear. You're going to need a lot of signatures. Usually it just doesn't happen, right? So if you need to see inside something that, is medium voltage, the answer is probably no. But for a lot of equipment, we're usually looking for a way to get inside there despite the fact that there's some hazard. And it's because we need to get a measurement, or we need to look at the status of individual components while the machine is running because we don't understand what's going on. So if we can use augmented operator technologies to see inside, even though it requires a little bit of engineering up front to preload that information, it can really help the users to do what they need to do in real time without exposing themselves to the hazards to begin with. So this is not something you're going to see in functional safety documentation, from ISO or from, the other standards that I mentioned earlier. Sorry, I'm not pulling up the numbers right now, but it is something that is very practical and that can really help improve our productivity and safety because of reducing the need to access the hazardous areas of the machinery. So another thing to think about too is planning ahead. And so what I mean by this is that there are technologies that can help us to do predictive or preventive maintenance that didn't exist a few years ago. So I was thinking about this a few weeks ago, and I know that if you ever end up on the side of a road with a flat tire, it's really a scary situation because you're right there in the highway trying to pull over. It's probably not an ideal place to be working on that car while you're so close to the moving traffic. So, but if you knew that the tire was going to go flat ahead of time, and I know a lot of cars have this technology. I have a 15-year-old car that tells me when the air pressure is low. Well, you can take care of it before you have an emergency on the side of the road. We can use that same kind of thinking when it comes to our machines, but in reality, we're not doing it very much. For many years, the industry has been collecting data because we've been using PLCs, HMIs, and SCADA systems, but we're not usually doing a very good job of taking the data that we have and using it to predict when something needs to be done soon. So this is really starting to change. And it's not really changing so much at the PLC, at the variable speed drive, and directly at the motor or the robot, but it's usually happening where we're taking the technology that we have and we're using maybe more cloud-based or PC-based or something local that we've learned from, where we take that data and we start to see operator efficiency. We start to see runtime data, and we know ahead of time that something's not right. And a really simple way to see this would be, if you think about a motor and a motor overload, we know that a motor, let's say the motor is rated for 15 amps. If it's running at 15 amps all day long, there's probably something wrong, because most motors are not operating at 100% of their load all the time. But really, that's not what we see in real life. Most of the time, a 15-amp motor probably runs at something quite a bit less than that, 12 amps that we might think is normal. It might be more like 7 or 8 amps. And we don't necessarily know until we actually build the machine and run it for some time period. So a lot of technologies are out there that can kind of look at not just the rating of the motor in this example, but they look at the typical usage. And they can compare it not only to typical, but typical for this time of day or for this temperature, for example. And they start to map out what's normal and what's not normal, and pretty quickly can figure out when something's not right, where the overload is not even coming into play. There's no alarm, there's no warning that we would normally have because we have not been using that kind of intelligent technology until very recently. So this is the kind of thing where when it comes to equipment failure at an unexpected time, oftentimes leads to unsafe work practices because somebody's doing an emergency repair during the middle of the day under a lot of pressure. And so again, this type of thinking is not what we have traditionally looked at when it comes to functional machine safety from a technology point of view, but it is good to give it consideration in a design and operation of a machine. How can we use these tools that are already available to help prevent a problem rather than react to it? So we talked about these things. Basically, the machine safety technology that is more traditional, that is around controlling access, using interlocks and sensors and light curtains, controlling specific hazards using functional machine safety designs that are designed to shut down a specific area, using logic to manage complex operations. Those are kind of the traditional ways of handling things. So when we look at those three areas, we can consider not only the safety, but also productivity. Now, using more IIoT, Internet of Things kind of technologies, where we're converging between IT and operational technology, we can start to see some benefits around not touching dangerous things because we have ways to see inside while it's running, and also predicting when there's a problem so that we can do controlled maintenance rather than emergency repairs. But it's also good to think a little bit about how to actually do this. And we only have a couple minutes to consider it, but this is pretty simple. Doing it takes a lot of time, but let's talk about that. So one of the first things you need to do really is identify what the hazards are. And this is an area that sometimes it's a problem for us. So as a person who's worked in tech support and as a product manager for safety-related products for the last 10 or 15 years, a lot of the phone calls that we get are from people who are trying to figure out something very specific that's not working, that's around a product or around a specific motor. And it's amazing how often the real root cause is that they don't really actually understand the hazard. So we address some kind of wiring issue, and we're not even looking at what causes the danger. So it's important in this area to look at the whole machine, to do a cross-functional team. So what really should happen is we need to think about what are the hazards, when do they happen, who knows the most about it. So a lot of times we think about the designer, the engineer knows a lot of this, but sometimes the person doing cleaning is the one that has exposure to a hazard, or it could be the installer, or even at the end of the life cycle of the machine, it could be in dismantling it. So we need to take a little bit more of a comprehensive look at things. In the industry, they use the word task-based risk assessment, and this is really what we need to do. What are the tasks, what are the jobs that need to be done, and what are the hazards associated with it? And that's when you do your risk assessment. Based on that, you can design the right equipment to protect people from hazard. So there are multiple standards that have different specific ways of doing risk assessment. And one of the things that is true is that there is no law, or even OSHA does not specify exactly which methodology we need to use. But we really do need to be using some kind of methodologies. So whether you're using 13849 or 62061, for example, which you can look up on your own time, the process usually goes something like this. We do what I just said. Identify the hazards based on tasks, and document those. Then you start to actually do your risk assessment, which is analyzing how much exposure does the operator have, how severe is the possible injury, how frequently does a person come into contact with it, and how easy is it or how possible is it to avoid the hazard when something's going wrong. This is numeric. It's not subjective. And at the end of that, you will come out with a very specific value that can be correlated to a particular level of hazard. And that is usually called a performance level. So in ISO 62061, they use performance level. 13849 uses SIL. And so you'll hear people say SIL 3 or performance level C or PLE. What those values are is not the design, but it's representative of the risk. How much hazard is there numerically? Once you've defined that, you can start working on your design. And these documents have guidelines to help you steer you in the right direction when it comes to the particular design you need. Do you need redundancy or not? Does there need to be continuous monitoring of all of the safety-related products by the control system to determine that everything is operating correctly all the time? It depends on your performance level, and then you pick out a design that corresponds to that. Once you've done your design, it needs to be validated and verified, and then you can document that. If you're building a machine that is going to be sold and needs to meet a specific standard, then you can provide the documentation to prove that the design meets those standards. So this is a typical methodology to do that. So in conclusion, I know this was kind of fast, high level in some areas and maybe a little detailed in others, but what we need to do is keep in mind that safety is the most important thing, but we also want to be productive. Obviously, OSHA is the organization that we're most concerned with when it comes to compliance. We must do that, especially as employers. Machine builders who are building machines for others need to think about it too in order to be competitive. So we also want to make sure that we're keeping productivity of the end user in mind in our designs, because as soon as we start to hurt their productivity, we know what's going to happen. They're going to bypass our safety designs. And now we've done nobody any good. We built something that was safe. Now they dismantled it because they don't like what it's doing in productivity. So it's important to consider both. And the best way to do that really is to think about things from, take a step back, look at the whole machine, and get a cross-functional team to help with your risk assessment. It always gives you the best results. Now, Schneider Electric deals with all areas of machine design. So we have all kinds of connected products that are able to sense the conditions, respond to it. We have products that are very involved with the control, as well as apps and analytics that are really designed to help evaluate the machine productivity, the plant productivity, especially when we looked at some of those things related to the IIoT, Industrial Internet of Things. Look to your supplier to help you with a lot of those technologies. So that pretty much wraps up this part of the discussion, and I'll turn it back over to Bob.
Thanks very much, Jacob. Nice presentation, and we'll be getting on to our questions here in just a moment. If you have some questions for Jacob, you can type them into the Ask a Question box on your screen, and we'll get to as many of those as we can. Within a few days, this presentation will be available for on-demand viewing. We'll post the archive on the Plant Engineering website. We'll send you an email message with a link connecting directly to it and to related resources when it's ready. So we've got a number of questions coming in for the presentation, and one question start out with from Mohammed Salim from Tenneco. Is there any guideline to determine what category of stop is required for a particular application?
Yes, there are. It's not always simple. You have to do the risk assessment first. So if you're using 62061, which is very electronic in its approach, or 13849, those are the ones I'm most familiar with. They're each going to have something that points toward the risk assessment. And if you can use stop categories 1 and 2, which relate to controlled stop, it usually means that the risk either requires that the machinery be controlled during the stop to actually help with the safety, or that the hazard is, I don't know how to say this, but kind of low enough, the risk assessment results are low enough where controlling it for a time period does not increase the risk. So it's not a simple question to answer, but yes, you do have to go through the risk assessment to get to the point where you're determining the stop category.
Yeah, and this is probably a good question that ties into that from John De Silva. Does OSHA specify in its regulations that risk assessment is mandatory?
Yeah, it's not a super easy question. Yes and no. OSHA does have guidelines that directly relate to machine safety, and especially around some of the most hazardous machines like presses. They're very specific about it. So many times, yes. What they don't usually do is point specifically at other organizations that you must use this one or you must use that one. So it's going to depend a little bit on your application. in most cases. You have flexibility in that. But in all cases, if the hazard is pretty high, like something better, more than still 1 or PLA, to be specific, you better do some documentation in your risk assessment, or OSHA's not going to like it. You're going to have to prove that you've done due diligence.
And another question in that area is, when is digital override of a mechanical e-stop permitted?
Don't really know how to answer that question. Usually not. If it's an e-stop, it's got to be an e-stop. If you're allowed to do a digital override, I question whether or not there's a very big hazard there at all. So I don't know if there's some exceptions. I know in the semiconductor industry that they have applications where it's not called emergency stop. It's a 3-letter acronym. It's EMO, I think. I usually have it off the tip of my tongue, but it has some exceptions in there that it's a little different than an e-stop, and there's some electronic actuation possible. Like, for example, I think they're talking about like using an HMI to hit stop, not usually permitted in an e-stop.
Very good. We've got time for a couple more. For your step 3 that you noted in the presentation, can lockout tagout be done with a safety PLC?
Yes and no. The PLC cannot really be locked out. So the safety PLC is really there to deal with safety while the machine or process is operating. Lockout tagout is if somebody actually has to isolate, dissipate the energy, test, do the lockout tagout procedure, and it's not. I kind of see these things as being unrelated, even though they're in the same equipment, because the PLC, the safety PLC, is for operation. Lockout tagout is for when you're shutting it down to do something. And I have never seen somebody do lockout tagout directly on a PLC, but for sure you're doing it on the motor, or the power that goes to the motor, for example. And yeah, it's controlled by the PLC, but at that point, there's nothing the PLC could do to it anyway because you've locked it out.
And our final question for this afternoon, can vision systems be used for industrial safety?
That's an interesting question. Vision systems, yes, it's already being done. So the area where we see it the most, I think, probably somebody will correct me if I'm wrong, but with automatic guided vehicles and robots, because some vision systems are capable of being integrated into the safety to prevent, for example, an EGV into running into a person. And but the trick with that is that it's relatively new technology, so some of those standards are still emerging. It usually means that the designer is going to do a little bit more work when it comes to the testing and validation of that, because it might not be fully defined, and the products themselves that are being used by the vision systems might not have a certification that you can point at. So it's usually going to have to be tested as a system.
Very good. Well, I want to thank Jacob for his great expertise here this afternoon and sharing that with our audience. I also want to thank Schneider Electric for sponsoring today's webcast. And now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends, so please take a moment to complete it as we use this information to improve our webcasts. So on behalf of Jacob Kimball from Schneider Electric, on behalf of CFA Media and Plant Engineering, I'm Bob Vavra. Thanks for attending this afternoon's webcast, and have a great afternoon.